This tutorial will illustrate how the CSI load optimizer can be used with a SAP 2000 model. In this simple 3-story by 3-bay planar frame example, we wish to remove column 4. In order to do this, we will lift the other columns at their bases until the axial force in column 4 is 0. The displacement of the column bases will be the variables, and the axial force in column 4 the goal. When using the CSI load optimizer, there are 3 classes of problems that can be solved. Optimization, where the number of variable loads exceeds the number of goals. Determinant, where the number of variable loads equals the number of goals. And best fit, where the number of variable loads is less than the number of goals. Because we have 3 variables and 1 goal, our example will be an optimization problem. This is the axial force diagram for the dead load case. Note that the maximum axial force is 2.46 kips in compression. A right-click on column 4 shows that the current axial force at the top is 2.195 kips. We will set a value of 0 for our optimization target goal at this location. We start by defining load patterns that will be used to assign the column base displacements. We will have a total of 3 called lift column 1, lift column 7, and lift column 10. Note that we also have a dead load pattern with self-weight. Next, we select the base of the first column so that we may apply a displacement loading. Using the lift column 1 pattern, we will assign a displacement of 0.001 in the Z or up direction. The displacement will be scaled when optimizing to reach the target axial load in column 4. We repeat this process at the other 2 columns we will be lifting. Next, we will create a linear load case where we combine the dead load case with all 3 of our column displacement cases. We will call this case dead plus lift. We will assign a factor of 1 to the dead load case, but the displacement cases will all have a factor of 0. The actual factors required to reach our target force will be determined by the optimizer. Before we start the CSI load optimizer, we will switch to the standard solver. Using the standard or advanced solver for optimization may yield faster solutions. Next, we move on to the optimizer, which can be found under Tools. The name shown on this form is appended onto the main file name to indicate a load optimizer file. The load case type for this example is linear static, and the load case will be dead plus lift. Note how the load assignments table is automatically populated with our displacement variable loads. We need to switch the dead load case to fixed, as the dead load should not be one of our variables. Next, we will define our goals, which for this model will be axial load at the top of column 4. And J is the top of the column. Our target value for the axial load will be 0. Note that we now have 3 variables and 1 goal. We can now click the Save and Run button. This will start the optimization. Note that LOPT1 has been appended to the file name to indicate an optimization case. Optimizations can take significant time. This message lets us know that the optimization is complete. The current display shows the display shape for the dead plus lift optimizer case. It is obvious that columns 1 and 7 are lifted the most. Next, we will switch to a display showing the axial loads for the case at the end of the optimization. Note that LOPT1 has been appended to denote a load optimizer case. Right-clicking on column 4, we can see that the axial load is virtually 0 at the top, which was our target. Having 0 load on the column allows it to easily be removed from the structure. Next, we will modify our optimization so that the axial load in column 7 will not exceed 3 kips in compression. We do this by returning to the CSI load optimizer, opening our previous load optimizer file, saving it with a new name, and then adding a limit in our goals and limit area. Here, we will specify that the axial force in frame 7 should be greater than or equal to -3. We click the Save and Run button to start the optimization. We will now switch the display to show the axial forces for our second optimization case. We can see how the axial forces have changed in the second optimization run. Column 7 is now limited to 3 kips in compression, while the lifting forces in the 2 outside columns have increased to compensate for column 7's decrease. Remember that the axial forces in the columns cannot exceed the dead load of the structure and must satisfy equilibrium. This completes this tutorial on the CSI load optimizer.